Okay, in this video we're going to look at two different examples. We're going to look at example 4-18, which is identical to example 4-16, where in 416 we used the Euler formula and turned it into a design equation for rectangular and circular cross sections. So we'll look at example 418, then we'll look at example 419. So 418, for a round section, to write a design equation, we go get from earlier in the section, earlier in the chapter, which is 4-46. Go take a look at that equation. We'll simply take the area term showing up in that equation, and we'll take the moment of inertia term showing up in that equation, or we're going to take into account the relationship between radius of gyration and moment of inertia. Plug all that together, solved in terms of diameter, and then we'll solve the Johnson equation for diameter in terms of our expected load, in terms of length, and in terms of infixity, Young's modulus, yield strength, those kinds of things. That would be a design equation if we're in the Johnson realm. For rectangular sections, of course, the cross section is described by two numbers, b and h. With one equation, we can guess one of them and we can solve for the other and see if we like the design. Again, as in example 4-16, we're presuming that h is a smaller number than b. The most important thing we're assuming in this example is that h goes into the cubed term for moment of inertia. Moment of inertia of a rectangular is bh cubed over 12. And so we are putting the h in the cube term and solving for the one that's not cubed in the moment of inertia. So we've got to make sure we've got our moment of inertias oriented properly. Again, plugging in b and h for area and moment of inertia terms, and then solving the equation for b only in terms of h and Young's modulus and infixity and yield and load and length, all of those things. We have a design equation that will give us b. That's the end of example 4-18. Now 4-19 puts that to work, and it says, choose a set of dimensions for a rectangular length that is to carry a maximum compressive load of 5,000 pounds. Here is our material yield strength, 75 kpsi. Modulus of elasticity is 30 million. Again, we want to use a design factor of 4. And we have an end condition of 1 for buckling in the weakest direction. And we're going to come up with the design, first of all, in Part A for a column that has a length of 15 inches. And then we're going to come up with a design for a column that has a length of 8 inches. It may be that the 15-inch version is more Euler-like. It may be that the 8-inch version is more Johnson-like. We'll see. And we're going to have a minimum thickness of 1/2 inch. We're not going to let dimensions go less than that. And so now that we have two different design formulas, we can either use the Euler design formula and then check, and we can guess that and see if we're right, okay? Or we could use the Johnson formula as a guess and see if we're right. If we guess wrong, then we have to calculate the other way. If we guess that we're Euler and we're wrong, then we do a Johnson design. If we guess that we're Johnson and find out that it's wrong, we do an Euler design. That'd be the process. So, first of all, dealing with the longer column, the 15-inch, also recognizing that with a 5,000-pound load and we want a design factor of 4, that's going to be 4 times 5,000, or 20,000-pound load. So, for the material properties given, our limiting slenderness ratio is an 88.9. So we're going to use that limiting slenderness ratio. Bigger numbers than this would be Euler beams. Smaller numbers than this would be Johnson beams. Okay, and so first thing we're going to do is we're going to guess a value of H of 0.375, and then we're going to use either Euler or Johnson to find out if we are to do design. In this case, we may have guessed Euler and gotten a B of 3.46. And then when we plug in both H and B, we get a slenderness ratio of 139, and that confirms Euler. Then we try, and we get an area of 1.298. Now we made another guess for H. We may have used the Euler formula, customized for design, to get this value of B. and find the L over K. It's 104, still bigger than the 88.9. And so if we guessed Euler, then we are still Euler. Then if we guess Euler again using an H of 0.625, then Euler would have given us something, but that L over, whatever it gave us, that L over K would not have fit Euler. Okay, so then we use Johnson, and we plug into the Johnson design formula the value of H, and solve for B, and take that HB combination and check our slenderness ratio, and we get an 83, which is less than 88, confirming that this one is Johnson. And then the final one is guess at 0.5625, and this one came out Euler, giving a 1.03 and an area of 0.579. Of all of these, it looks like the 0.625 has the smallest cross-sectional area, which is the minimum material use, and so we would go with the 0.625, and if we prefer standard sizes, we wouldn't use the 0.76. We would either round up to the next standard size, but let's think about what's happening here. 0.76 is definitely safe for buckling for the 5,000 pound load. It's just not quite safe for a 20,000 pound load. Rather than going up to the next standard size, we could drop down to a 0.75. And what we would learn is that our design factor, or our factor of safety, is not quite the 4 that we thought it was. It may only be about a 3.95, but I think that's a reasonable exchange. We'll go with a slightly smaller standard size, and we'll only have a factor of safety of 3.95 instead of 4, but I think that's probably fine. This is the work that was done using a 15-inch length, as the problem statement said. Now we repeat all of that for an 8-inch length. And they don't show the results for an 8-inch length, but they say using that similar approach, minimum occurs with a 1/2 by 3/4 inch rectangular area.